Now for the states of matter, you need to be able to remember which each stage or state is and their properties. So gases, are free to fill any space available. If you release a gas, let's say you've got a balloon and you pop the balloon and it's got helium in it, that helium's going to, spread out all over the room. And yeah, that's in contrast to liquids where the liquids are free to move among themselves, but they do not separate out like gases. So liquids are a fluid, just like gases are a fluid, but they're two different states of matter. Solids are about fixed positions. They can't migrate to other places. So, if you drop a block on a table, that block is going to stay together or break, right? But it's not going to conform to any shape. And then plasma is at very high temperatures, consisting of ions that have electrons, whizzing around. And so plasma, we've got that. And then the one that's not listed here is Bose-Einstein condensate, which is a state of matter that's at very, very cold temperatures, and it's a quantum state. Now, with phase changes, it's important to remember that as you add heat, it is increasing, or it's not increasing the kinetic energy of the molecule, so the temperature is the same. That's a key thing. And then, but what it's doing is it's breaking the close bonds. So in a phase change, for instance, if you've got liquid water and it's becoming a gas, let's say it's 100 degrees Celsius, those bonds that have to be broken are quite difficult because it's in a liquid form, and then to get a water molecule on its own breaking out and then going as a gas, it's not easy. So that's what happens in phase changes. We looked at this graph. We used this graph where we looked at how when water turns into steam, temperature stays at 100. Water and ice. So in other words, if you're melting ice, and here's the ice cube with the melting water, both are at 0 degrees Celsius. Both are at 0 degrees until it completely becomes water. Once it completely becomes water at 0 degrees, then the temperature can start to go up if you keep putting heat into it. And so that's like if you've got ice in a glass, and then that water and ice are at 0 degrees until that all becomes water, and then it can start to go up to room temperature. So the latent heat of fusion is 333,000 joules per kilogram, and that's to take 1 kilogram of ice and turn it into water at 1 kilogram of water. And on your equation sheet, you have Q equals MLF and MLV. MLF is latent heat of fusion. Fusion is dealing with liquids and solids. And then vaporization, LV, is dealing with the vaporization. So let's go ahead and practice this one real quick. Go ahead and pause the clip, and when you're ready to check, you can hit play to continue. All right, so should get 166,500 joules as the energy or the heat that it'll take to melt half a kilogram. Vaporization is for water, it's a much more difficult process to, if you've got water at 100 degrees Celsius and you want to turn that into steam at 100 degrees Celsius, it's going to take you 2,260,000 joules to do that. And that's because it's harder to break those bonds and make those turn into gas. So again, latent heat of vaporization here, and you can think of vaporization, right? You're making it vaporized, a gas. So in this one here, we want to know how much energy does it take water at 35 degrees Celsius to turn into steam at 115. So this is a 3-stage process. Forgot to put how much mass. It's 3 kilograms. So you've got water that's at 35 degrees, and we're going to put heat into it. And when we do, we've got to get it up to 100 degrees before it'll start to melt. Start to vaporize. So that's the first step. Now, once you have water that's at 100 degrees, and if you keep putting heat into it, it's going to phase change. Then eventually you'll get 100 degree steam. Then the final step is you have 100 degree steam, and you want to get that to be steam at 115. So that's the last process. Now, for here, you're dealing with specific heat. Here you're dealing with specific heat, but here you're dealing with latent heat of vaporization. So what we want to find out is what is the total amount of energy to make this happen. Now we know the specific heat of water is 4186. We know that the specific heat of steam is 210 or 2010. And so yeah, go ahead and work through this and solve through this, and then when you're ready to check, you can hit play to continue. All right, so for the first one, we should get 816,270 joules. For the second one, we get 6,780,000 joules, and then the last one 904 or 90,450 joules, and a total of 7.7 times 10 to the 6 joules to make that happen. All right, so I showed a reclip of the Dorito that was burning, and we talked about what kind of reaction that is, and it's exothermic. Xing, going out, so that chip is burning, it's releasing energy. And then I showed the video where they mixed those two chemicals together, and it was on the top of that block that had some water on it, and it was endothermic. It pulled energy in, so it actually froze that water as it cooled, and cooled the surroundings because it pulled heat in to make the reaction happen, and it got quite cold, and so that's endothermic. So it's important to remember these two definitions. Exothermic is releasing heat. Endothermic is absorbing energy, and it pulls heat in and cools the surroundings. Another thing we reviewed was the second law of thermodynamics. If you took this glass and that broke, and let's say you threw it back into the air and then it landed on a table and it was the original glass, we would never see that, right? And we know that all natural processes go to more disorder. So although it would not violate conservation of energy, there are things that we see in nature that just don't occur. They don't break any laws, but we don't see them. And so this falls under the second law. And another thing that we never see is that heat going from a hot object to a cold object, the reverse, where we don't see, hot or heat going from a cold object to a hot object. We always see it going from hot to cold. That's because that hot object's moving around faster. It bangs into the molecules of the cold and makes those start to move faster. And so that's the way that heat always goes. And then finally, we never have a 100% efficient engine. To have that, we would have to have all those molecules in a steam engine or a combustion engine all line up perfectly, pushing the piston over and using up all their energy so that their final temperature is 0 Kelvin. And we are far, far, far from that. Really, in an engine, the molecules are going all over the place, pushing the piston over. We're never going to have a 100% efficient engine.